So next we'll hear from Brian Keating talking about some of the experimental evidence for inflation.
Okay, so I am the token experimentalist on the panel tonight. So I brought with me my own baby universe. I hold in my hand an actual universe. And in this universe, Sheldon's not wearing a shirt at all. It's the most popular one of all. Okay, so Andy gave an excellent introduction to these deep and mystical theories that seem to be both in vogue and quite speculative, but at the same time may have tremendous impact, just as the Big Bang Theory was a pejorative. The name itself is a pejorative, but is now accepted by all but a few people in certain parts of the country as being exact description of nature. So now maybe it's not so crazy to think perhaps we do live in a multiverse. So I want to talk about this. Andy showed this slide. This is a famous woodcut from the 1500s when they just had invented Photoshop. And what it depicts is this ancient quest. Cosmology is a very easy science to do in one sense because you can do it with just your eyes and your brain. And in fact, that's how early humans did it. That's the oldest science. People looked up and wondered. And this depicts this character looking back in space, and as Andy said, your eyes, just like a telescope, are time machines. So you can look back in space, you're looking back in time. So things that are far away from us, this artist who conceived of this woodcut was conjecturing what they might look like. Now this looks not too dissimilar from some of the Escher paintings and woodcuts that we saw at the end of Andy's talk. So how crazy is it really to speculate about such things? And it's really, as I said, one of the oldest quests of humanity. Here's a more modern depiction of it that I've stolen. And this depicts sort of a very crude space-time diagram that shows things today down here, and then in the past, this beach ball flattened out and laid flat as if you're God looking down on this region of the multiverse. And the preceding epoch to when these most ancient photons left the primordial plasma. That epoch, we believe, is called inflation. I'll talk about that because the hypothesis is that if inflation occurred, as Andy mentioned, in many models of inflation, it still is continuing, it still exists, and it has so-called eternal inflation. You cannot shut it off. In that case, there may be an infinity of universes, and in fact, this diagram may be wrong. There may be no dawn of time, and we may be back to the old Aristotelian and pre-Aristotelian notion that the universe is infinitely old, and that baby universes perhaps spawn cyclically into and out of existence. I'll spend a lot of time focusing on discoveries that we made using this image and images like it with our telescope at the South Pole called BICEP, and how we infer from the properties that we see here what this epoch might have been like. And then the logical extrapolation that you must make is that if this occurred, if this inflationary epoch occurred, then perhaps something like the multiverse must also be mandated in some theories of physics, both from a coupling of the inflationary high energy physics of the early universe and also things like string theory, as Andy mentioned. This has attracted a lot of attention from worldwide organizations. This is on the front page, our discovery with BICEP 2, the so-called space ripples of the Big Bang smoking gun. So I always like this headline down here from The Economist. Sounds like some guy just suddenly sees the start of the universe. Wow. If you're looking in one, I saw it. It's like a meteor. And then, of course, the best newspaper in all of science is, of course, the UCSD Guardian, which is a little bit more circumspect and very calm in their notion. They said, UCSD scientists prove inflation theory. Well, that's pretty awesome. I don't think you can even prove a theory in physics, let alone the fact that we did it all by ourselves, which we didn't. So I'm going to talk to you about this, and I always say it's a mystery. It's a mysterious universe in which we live. There's a mysterious galaxy not too far from here where you can buy David's books, but there's also a mysterious multiverse. And so I don't want you to ever come away, especially I see a lot of young people in the audience, and that's wonderful. I want you to come away with the notion that there's way more to do than has been done. And the people that are up here really haven't even scratched the surface. And it's your job to come up not just with the theories and the conjectures, but actually follow through with it. Learn the math, learn the science, learn the physics, build the experiments, travel to these distant places. That's what I want to inspire you guys to do. And even we have some older people that could be inspired to do that too. So I always say it's a mystery, and the mystery, like all great mysteries, you can maybe phrase it in the form of a murder mystery. And I'm going to lay out a few different of these bullets, and I'm going to hopefully motivate the fact that there is evidence that inflation occurred. And then following on from Andy's talk, that perhaps if inflation occurred, there too, therefore also did the multiverse. The multiverse somehow follows from this explanation. But I'm going to leave in a little wrinkle at the end, so I want you guys to stay tuned. I'll wake you up for the end. So I'll talk about the scene of the crime where we go and what the very early universe was like. I'll talk about our crime lab where we built a forensic tool to appraise what the early universe must have been like. And then the so-called smoking gun, as the New York Times front page decried, that we seem to believe is indicative of this inflationary, explosive expansion of space-time. And then perhaps the jury's still out. There's still some controversy about our results and even some very interesting conjectures for the future. So just a very quick diagram. This is probably the most technical diagram I'll show. This is a slide that our collaboration put just to demonstrate the major features of cosmology in one slide. It's very difficult to do, but nevertheless, it starts with a Big Bang. At least our portion of the multiverse, or in the region that when I was a kid, there was only a universe, okay? So I have to get used to it, just like when I was a kid, there were 9 planets. But then people like Adam Burgasser and others came along and killed off Pluto. And so now I have to always correct myself that there's only 8. So we talk about the Big Bang as being the local origin of, as Andy said, this observable universe that we can detect that's roughly 40 plus billion light years across. That instant is called the Big Bang. Time equals 0. So you set your watch, and then roughly a trillionth of a trillionth of a trillionth of a second after that came this violent expansion of space-time called inflation. And then after that, things and events are listed here that are a little bit more prosaic in terms of their impact, but they're all observable relics. They all produce relics that we can see today, even if they're not in the form of light. We can detect the processes, the fact that we observe elements today, light elements like helium and hydrogen. Those are relics left over from the Big Bang. Very little hydrogen can be formed outside of laboratories. So what we see is residual primordial evidences. This is trace forensics from the Big Bang itself. When the protons combine with electrons that were around since the very beginning, then the cosmic microwave background, or CMB, is formed, and this is this famous 3 Kelvin background. It's depicted here when a globe of the sky flattened onto this beach ball. And this depicts what you'd see with your eyes if your eyes were sensitive to microwaves and you looked out at the night sky. You wouldn't see constellations, you wouldn't see stars, planets, or galaxies. Instead, you'd see fluctuations in the microwave background's temperature, its intensity, and its polarization. And that's this epoch here. And so what we're trying to do is use this image that we've made and other groups have made of the very early universe, 380,000 years after the Big Bang. Take this image and use it as a type of film. Okay, so it's a little bit strange to think about light being a film, and nevertheless we have to think about it in that way. We're attempting to expose waves of gravity on these photons. Okay, so probably half the audience doesn't remember film, but half the audience does. So a film was this ancient thing that we used to use 10 years ago to take pictures, and it would expose light. Here we're not exposing light, are exposing gravity, waves of gravity, gravitational radiation from the inflationary epoch on this background. So it's as if we're looking at this beach ball, and what we're trying to see are not the temperature fluctuations themselves, but distortions and ripples. This thing is wiggling like a ball of jello, and those wiggles are imprinted by waves of gravity. Those waves of gravity are produced during the epoch we call inflation. We built a telescope to do that, and in doing so, we were guided by the fact that we've confirmed many of the predictions of inflation. Andy mentioned a few. I'm not going to go over them. But inflation is one of the most well-tested, if not proven theories, despite the UCSD's Guardian headline. It cannot, in some sense, be proven, but even to the extent that we can understand ways to falsify it, it's been passed with flying colors. So we can't say that we've proven it unless we can rule out every one of an infinity of possible alternatives. But in this case, we have so much credulity in the model that it behooved us and myself to invent this experiment to go after this unique signature of inflation called gravitational waves, that produce so-called B-mode polarization. So we're looking at this pattern of microwaves. They have polarization properties associated with them, just like polarized light reflects off the ocean surface. You can use polarized sunglasses to see it. And we're looking back at this pattern to see waves of gravity exposed from the very earliest instances after the Big Bang. So what is the CMB? I want to show you this, just a kind of cartoonish glimpse. So if you go out into low Earth orbit, and you looked and your eyes were sensitive to microwaves, this is what you'd see, an amazing depiction. The beauty, the grand elegance, if you're a religious person. This is the face of God. It's so beautiful. No, this is what you'd see to first approximation. You'd see nothing. It would be this uniform, boring, puke orange glow that your eyes would detect no discernible pattern from. This is the so-called 3-degree Kelvin microwave background signal. This is the primary tool that precision cosmology has been used to extract the parameters of the very early universe. Now, if you take away the average level that you see in each direction on the sky, you're left with these fluctuations like on this beach ball. And this is quite an exhilarating map to see. An image like this was called by Stephen Hawking like looking at the face of God. Ironic because he's a devout atheist. But nevertheless, looking at these images, looking at these patterns, we've refined our understanding of the global properties of the universe, its age, its mass, its energy, its possible future evolution. It's just incredible to think of everything we've accomplished just with this, and now we've endowed it with another observable called its polarization, which I'll talk about briefly. So it was discovered in 1965. So I always say it's the last great discovery in astronomy from northern New Jersey. I'm a New Yorker, so I'm entitled to make fun of New Jersey. And it was discovered actually serendipitously back when this was the entire internet. So Steve and Sue and Cindy are here from Viasat. So this used to be the entire internet. It was one satellite that communicated around the entire Earth. You bounce signals off of even more slowly than you could do with an old 300 baud modem, and you'd be able to communicate with it. But when they launched it, they found they couldn't get rid of this glow in the background that seemed to come from all directions, and that, of course, turned out to be this 3 Kelvin or 2.7 Kelvin microwave background radiation. So that was its discovery. They won the Nobel Prize for this in 1978. And in the old days, I usually say to people, if you tune your television to a UHF station there's no signal, local signal, you would get static on it. But nowadays, no kids know what static is, okay? YouTube never gets static. But about 1% of the static on an old-fashioned CRT-type monitor would be from the Big Bang itself. So the orange glow that you saw originally was the background radiation. It's 3 Kelvin. Then there are tiny little fluctuations predicted by our late colleague Art Wolf, who was at UCSD, predicted that there should be fluctuations in the microwave background only 2 years after its discovery. Quite astounding prediction, and that was borne out in 1992 when the COBE satellite measured these imprints, these fluctuations in the microwave background for the first time. And that was later awarded the Nobel Prize in 2006 to George Smoot and John Mather. And those fluctuations led us to believe that there must be some force responsible for the fluctuations on the largest scales in the universe. Just to give you an example of how small, I say that these are large. So the microwave background itself is 3 degrees Kelvin. Subtract away 3 degrees Kelvin, you're left with fluctuations that are about 1 part in 100,000. How big is a part in 100,000? Well, the surface of a bowling ball, if you map the surface of a bowling ball and compared it to its average radius, the fluctuations are about a part in 10 to the fourth, or a part in 10,000, meaning that the surface of a bowling ball, which most people consider pretty smooth, is actually much, much rougher than the surface of the last scattering surface than this image would be if it were depicted as a bowling ball. Again, not my bowling ball, because I'm a terrible bowler, has a lot of dents in it. So the question is, where do these fluctuations come from? And the inflationary model has posited that these fluctuations come from quantum behavior in the early universe, in the fabric of space-time itself. So what are we trying to do? We're trying to take this image. This is now just a purple and blue. This is the actual COBE image of the full sky, laid out flat again. And we're trying to understand from this image that we see that dates to 10 trillion seconds. Sounds like a lot. It's 380,000 years after the Big Bang. We're trying to infer from that, what did the universe look like a trillionth of a trillionth of a trillionth of a second after the Big Bang? 50 orders of magnitude extrapolation from the physics of 380,000 years after the Big Bang to essentially right at the beginning of time. So what would that be like doing in more human terms, in a more human scale? So imagine you look at this creature over here. You biologists here will recognize this, and if you do recognize it, please come to Gattaca event on August 11th. This is what you look like 1,000 seconds after you were conceived. Okay, this is called a blastocyst. It's roughly 100 to 1,000 cells assembled into this nice little soccer ball package. And if you were trying to extrapolate what this image looked like by looking at, say, this handsome devil here, if you were looking at him and you were trying to extrapolate from this image, how could you possibly expect to do that? Okay, so here's David, our lovely co-collaborator tonight. So here he is at 2 billion seconds old. I think that's roughly correct. You guys can figure out how old that makes him in more human terms. Now imagine trying to do this, looking at a picture of him and inferring what his blastocyst looked like. I think he looks like his mother there. But this is only a factor of 2 million extrapolation. This is 50 orders of magnitude, 46 orders of magnitude more, and yet we think that we can do such a thing. And that has to do with the simplicity, although it's complicated, the simplicity, the elementary nature of space-time at very, very early epochs when the universe produced the CMB radiation that we see. So how do you do that? Well, it starts with a pairing of theorists and experimentalists thinking about ways that you could observe directly the signature of inflation. So what inflation predicts is that there's a background, just like there's a background of light, there's a background of gravitational waves. They come through space-time and they shake it and shudder it, and it causes tremors and reverberations. Those induce a specific kind of swirling motion in the polarization patterns that we see in the Big Bang. That's called B-mode polarization. For cognoscente, it's an analogy to the magnetic field, which is written as a certain vector operation. So we attempt to measure these little polarization orientations and their intensity on the entire sky, or at least on this patch of sky that we can observe. And the smoking gun has been called many times to observe this pattern. This is a simulation, and I'll show you later some real data, and you can compare for yourself. So how do we do that? We built an experiment called BICEP 1, and then we built a successor called BICEP 2, including the very hard work of my graduate student, John Kaufman, who's in the audience, who just became Dr. John Kaufman. This is a telescope which is not only one of the world's most powerful telescopes, it's also the world's most southern telescope and the coldest telescope in the known universe, and I'll explain why that is in just a bit. Here it is. If you ever see this picture, you're in really bad shape because this is sunset at the South Pole, which happens once per year in March, towards the end of March when spring starts for us. That's when fall starts at the South Pole. So you won't be getting out anytime soon if you see this beautiful sunset. It's a relatively large collaboration, although not compared to, say, a particle accelerator, about 12 or 15 different institutions. And we built this experiment. We started with BICEP 1 in 2005, and we upgraded to BICEP 2, and we have many more upgrades still to come. This is what the telescope looks like before it was shipped down to the South Pole. It's a refracting telescope. It's actually not that big. This length here is about 5 feet long. But the unique thing about this telescope is that we designed it to be cooled down almost to the temperature, in fact, to the temperature of the cosmic background radiation itself. So it sits at 3 degrees Kelvin. The warmest parts of it are at 3 degrees Kelvin. It sits on an ordinary telescope mount. It can scan back and forth, look up and down. It's quite simple. If you did a cross-section through it, you'd see, at least in the original design, it stands for background imaging of cosmic extragalactic polarization. Light comes in. It's a refracting telescope like Galileo used to first change mankind's conception of what the universe was like 405 years ago with the training of his small refracting telescope on Jupiter and on the moon. So light comes in, gets focused on detector. The detector arrays sit at a quarter of a degree above absolute zero. So these are cooled down to 453 degrees Fahrenheit. Sounds really cold. And in fact, it is. People wonder what the lenses are made out of. It's very simple. We use a very high purity version of what we used to have in these old milk jugs. I don't know if I've never seen one in California. Maybe they're banned. But it's just high density polyethylene. It makes a good lens. It's transparent from microwaves and induces almost negligible polarization contamination. So now where would you put such a telescope? Well, here's the Palomar Observatory. So if you converted before 2 billion seconds into years, you can calculate what year David was born. And I'll just tell you that he was born, so they built this telescope for David. This was built the year before he was born so that he could use it to think about the universe as he's done throughout his career. This telescope, though, was built and put in north of Julian, and it was done so for a reason, because in 1949, that part of San Diego was quite dark. And its background, what it's looking for is light. So you had to put it somewhere dark. We wanted to put our telescope somewhere cold because we're looking for something that is analogous to heat. So we want to take it somewhere cold. So we took it to Antarctica. And if you go out into space, you can look at Antarctica like this. And the center of the Earth's axis, the southern point on the Earth's axis of rotation, is the South Pole. And it's a continent. Antarctica is an actual continent. I actually brought some pieces of it home with me the second time I was there. But don't tell the governor. No, there is no governor there. It's a lawless continent. There's only about 1,200 people there at any given time in the summer. And right now in the winter, there's about 200 people. So the entire continent is popular with 200 people. So you can actually get to a lot of superlatives, I was thinking when I was down there. I mean, I've never been like, it's hard to be like the fattest person on the North American continent. But I could actually do it in Antarctica. I could be the fattest. You could be the shortest, the tallest. The oldest, the youngest. See, there's a continent of superlatives, including the fact that it's the highest continent, it's the coldest continent, it's the windiest continent. The South Pole sits at about 9,000 feet above sea level, so it's a little bit of the way into space, where you'd like to be ideally. If you go to this website in the summertime, you'll see a picture that looks like this. Right now it'll be completely dark, but there's a webcam that shows you what the weather conditions are like, and it's usually 100% chance of white. And if you think about it like a snow forecast, this is 9,000 foot deep base, if you think about skiing, okay? But unfortunately, it's all flat, so you can't really get too far. You can go cross-country skiing. We go there despite the fact that there are very known to be very hostile natives that live there. Despite that fact, we still went there. So it's a very dangerous environment, but some of my colleagues are here. They treat me worse than that. Okay, so when you go down there, there's no Walmarts, there's no Targets. You can't buy clothes when you're down there, really, besides souvenir T-shirts to give to your friends. So instead, you have to stock up with all the clothing you're going to use for the next month, 2 months, 9 months, or a year. You pack them into these bags, and you take all these articles of clothing, including these really cool semi-inflated moon boots, we call them, so that you won't get frostbite. If you wear normal sneakers, your feet will freeze due to the conductivity through the rubber. You catch a flight. Hopefully, if you wake up in the morning at 5 in the morning in New Zealand, you don't go outside and see this. But the first time I went down, I did. This is a C-130 cargo plane that flies from Christchurch, New Zealand, to the McMurdo Continental Base in the U.S. This is also 1/10 of the New Zealand Air Force. It's pretty interesting. Okay, you sit there. It's a beautiful, very spacious, lots of legroom. No, it's a terrible environment to be on. If you notice, there are very few windows, if any. The pilots have windows, thankfully. But there's only 2 or 3 other windows on the whole plane. There's no bathroom on the plane. You have a little pot called the honey bucket. Don't ask me why they call it that. And you're served, your first-class meal is in a bag of some mystery meat. And you sit knee to knee for, luckily, it's only about 11 hours, okay? So, but you build up a lot of frequent flyer points. And eventually, when we end up getting to the South Pole is quite a beautiful place to be, at least the first day you're there. Then it gets kind of monotonous. Some people love it. John Kaufman, he loves it. I get tired of it. You land, here's the passenger terminal, okay? This is the Admirals Club, President's Club over here. You pick up your light. Remember what this looks like, because you might see a picture of it later on. Okay, when the early original explorers got there 102 years ago, they skied up from sea level to 10,000 feet almost over waves of frozen snow called sastrugi. And as I said, up above crevasses and terrible, terrible environment. We make it there in 3 hours from the coast, even in the C-130s. And this is a sort of scale model of what they would have looked like in Photoshop. They weren't so happy, and in fact, Robert Falcon Scott said, "Great God, this is an awful place." And little did he know, he would die 2 months later trying to get back from the South Pole to his fuel and food depots. Nowadays, I say it's an awesome place. So this is the actual axis on which the Earth is turning. Pretty cool. So I can run around the world, and even for somebody slow like me, you can do it pretty quickly. But I say it's an awesome place because nowadays it has a kitchen, a greenhouse, libraries, a sauna, can you believe it? A half-size basketball court, and many, many other amenities. You have to prove to your mother that you made it there, so you take a selfie, and you start walking to work, and there's Bicep. So we built this observatory back in 2005. And here's the outhouse. And this outhouse, if you remember what the passenger terminal looked like, is very, very reminiscent of what the passenger terminal looked like. I'm always hoping they get that right. This is a site that also means they're going to spend the winter there. This means the sun is going down. The sun doesn't go straight down like it does here, roughly at some steep angle. It just grazes the horizon. In fact, you don't know where it's going to go down when you're down there. So it just circles around. You can barely see a tinge of green, not from the laser pointer, but you can actually see the green flash for over several hours when you're down there. This was taken by our winter rover the first season, Denis Barcat's. I always tell people, they're like, well, what's it like to be there? And I say, it's great, the pay is awesome, you get $75,000, and all you have to do is work one night. There's the sun going down. Okay, so what happened? What did we actually observe? Well, remember this prediction? This is a simulation. One of the nice things about making a big discovery potentially like this is that you get places like the Washington Post to do your graphic arts. So they did a simulation, this pattern taken of what you'd see if there were gravitational waves. And here, in fact, is real data. This is not a simulation. We can compare the predictions to what a simulation, very detailed simulation, would predict, and it shows exact agreement. So we have a great confidence in it, and moreover, the scientific community has spent many, many months, just 3 months, we've had over 600 different publications. Here's just a smattering of them. As of last night, there's 600 publications that are citing our results, dissecting it. This is what scientists do. They have to check and closely observe and make sure that they can confirm and reproduce your results. Otherwise, it's not scientific. So here are the results. The most gratifying thing was this article in the best science news journal there is, The Onion. It said, top theoretical physicists, R&B singers meet to debate the meaning of forever. So down here it says, we can observe long-term phenomena like the CMB, primordial B-mode polarization, and the love between India Ari and her man. All of which seem to have existed since the universe's infancy. And I want to make them change it to R and B modes because that's... Okay, so when you go back to this, we think that we've observed this imprint of gravitational waves produced by inflation. So if there was an inflationary epoch, what does that imply? Well, it implies, as Andy said, perhaps there's this infinity of universes called the multiverse. There's not necessarily a proof of it, but if this can be confirmed, it would be very strong motivation that perhaps something like the multiverse isn't too crazy. Just finish up with a couple questions that I will want to ask David and Andy later on if you guys don't ask. So what can you say about religion? This quote from Paul Davies is quite evocative. I'll just get cut to the point. He says that the multiverse at a certain level seems to be, at least in the anthropic or finely tuned versions, seems to be reminiscent of religion. Not as a pejorative, but just seems to be philosophically at least isomorphic in some sense to a religious theory, or to a religious concept rather, not a theory. So this is a very interesting article that I encourage people to read. Getting back to Galileo, what can we say about the God and the universe? So I just say stay tuned. If he had a big bicep, perhaps he wouldn't have faced the Inquisition like this. And I thank you very much and see you in November, hopefully.
Brian, you've talked about discoveries of empirical evidence through cosmic background radiation, gravitational waves of the Big Bang. What physical evidence might we achieve someday to demonstrate the reality of multiverses?
Yeah, so there are different classes. So the question was what other types of empirical evidence might prove or motivate the fact that there might be indeed a multiverse. So there are different levels of predictions and models that predict startlingly obvious signatures. David actually showed one where you have these two circles on the sky in opposite places, and people have looked for that, those signatures in the cosmic background radiation as well, seeking to perhaps detect the collision between two of these baby universes within the multiverse. So that's perhaps one of the most obvious ones. Then there are different levels of credulity if you're willing to accept the notion that a discovery of gravitational waves proves or motivates inflation, and that inflation must be difficult, if not impossible, to stop, that it must be going on everywhere. So even though we might not detect these other universes, similarly, we believed 100 years ago that atoms were the most finely grained substance that we could possibly detect and observe, and the laws of nature were as we knew it back then. Now we know much more. So I think we'll winnow down the possibilities first, and then we can delve into potential other observable signatures. But I should say that it's motivated equally well from inflation theory and string theory, and I don't know of a way observationally to prove it from the string theory side.
There are some ideas, very speculative, in these versions of string theory where you have these large extra dimensions, like these brain world scenarios that David was mentioning. We have some evidence that's very intriguing. This is the idea of so-called dark matter. It seems like there's a lot of missing mass in the universe. And some people speculate that one way of explaining this is that it could be due to the gravitational influence of other brains farther away. I don't know if this is correct, but that's the kind of a thing where maybe there actually already is evidence out there for other universes, and we just need the theoretical and philosophical framework in order to really elucidate that.
Yeah, I think the notion that there might be brains next to ours, we already have as one of the theories that gravity can leave our brain, whereas some other forces can't, in which case we might be feeling another brain above, another below, and wouldn't they cluster their galaxies near ours too by the gravitational influence? And this would explain some of the effects that we see in our galactic rotation. If I might also add, those of you who are artists, I didn't mention it, if you're interested in pursuing any of these ideas for possible performance art about the multiverse, get in touch with Sheldon Brown or any of us, care of the Clark Center.
Yeah, great. Can we move the microphone around throughout the room, please? Okay. We'll start over there. Yep.
Hi, and thank you very much. I thought this was all fascinating. I have a question. I've been studying this for about 30 years, and I'm just wondering if any or all of you may have looked at this from a slightly different direction, which is basically from the direction of the golden ratio, the Fibonacci sequence. Having looked into that, I found it fascinating that just about everything that's considered beautiful or balanced is based on that ratio, about 1.61 something. And the more I looked into it, whether it's the arrangement of the pistils of a sunflower or the curvature of the nautilus, sea nautilus, or the curvature of the human ear or the spiral nebula that you look into, or the curvature of a wave, all is built on this same ratio throughout nature. And I think in 2003, which is where I'm going with this, if I'm not mistaken, French cosmologists had deduced that the actual shape of the universe was a dodecahedron, which again is built on this same ratio, which you would think is an artificial shape. So in getting into multiverse theory, I'm wondering if you've looked at that ratio, what role it could play in all of this, and having a descriptor for what this all looks like and how it fits together.
I've not looked at that. I don't know. Have you guys looked into that?
Well, it occurs to me that we like it in part because we're constantly perceiving us around us, and that natural phenomena that are additive processes, like the creation of crystals, the creation of branches on a tree, that these would tend to follow a Fibonacci sequence if they're adding in a relatively moderate way. So it may be, it's just the matter that when nature adds things to adding things to adding things, that it occurs a lot, and we find it pleasant because it means that whatever's going on is healthy. That's just a speculation. That's just a sci-fi.
And one quick follow-up question to that is that I don't know if any of you have seen I think it's a somewhat famous picture on the internet, but they did a slice of a mouse's brain and illuminated it, and then they overlaid a picture of the universe, and it was nearly identical.
Well, one of the things that's been out lately is if you take a look at the Sistine Chapel, and if you look at the funnel singularity hole that God is emerging from with his cherubs, with his hand to give the spark of life to Adam, it's shaped exactly like a human brain, with the filigrees coming off exactly where the cerebellum is, and his hand coming straight out of the prefrontal lobes.
Interesting. Yeah, my student John Kaufman. Thank you for the question. My student John Kaufman is a student of this type of art in the microwave background, and he actually found a very distinct picture of a rabbit in our data set. It's quite beautiful. Can we pass the microphone around? Cosmic rabbit hole. Maybe in the way back. I see someone who's had her hand up for a long time.
So if there were specific requirements in terms of the constants and the laws of physics that were required for life to begin in our universe, and there are also other multiverses where laws are different, how could other universes support life?
Maybe Andy, you can address that.
So we really don't know very much, as much as we would like, about how likely life is to come into existence. What we can say are things that we think are crucial prerequisites for our kind of life. And you can make some pretty plausible arguments for what are the kinds of prerequisites you need for life in any case. For example, you can have parameters like of cosmology where the universe collapses after a fraction of a second. I don't think anything's going to happen very interesting there. And you can have the universe expand and accelerate so fast that everything just becomes empty and all the matter is diluted. I don't think things are going to happen there that are interesting. So it could be that if you looked at this whole multiverse, by some measure, most of the universes are really uninteresting from our perspective. Maybe most of them don't have life at all. And so this is still an open question. We actually really don't know how to do statistics, especially.
Sorry.
Oh, go ahead.
Could there be other universes that don't necessarily support life but have things like similar solar systems, planets, stars in the same kind of way that we do?
It's certainly a possibility. Because we have a real lack of knowledge here, we know things that are necessary conditions for life, like having a planet, but we don't know what the sufficient conditions are. So we don't know how likely it is for life to start, for evolution to get going. I personally think it's quite plausible that you could have a universe with planets, but life didn't evolve. It really depends on the answer to open questions which we don't understand about how likely it is for self-replicating molecules to kind of get going.
Yeah, what you're talking about to some extent is what's called the Anthropic Principle. And that is, it's no coincidence that we observe that we're in one of those universes that had the conditions necessary for you to have life. Because nobody's in those other universes to notice that they're in a sterile universe. What the mind then starts doing is saying, what's the ratios? Are there gazillions of sterile universes for every one that gets people sitting on stage asking silly questions about parallel universes that they're never going to see anyway? Well, that's where Lee Smolin comes in. Because if there's evolvability of universes and this multiplicity of universes, the laws aren't random, but they're inherited and refined by evolution, then the vast majority of our sister universes have fecund life in them. And a majority of them have at least some bipeds in auditoriums talking about this. And if you dispersed it out across the infinite space, some of those bipeds will be wearing mostly black and answering questions from somebody wearing white.
Thank you. I can't, maybe we'll move it up somewhere in the middle there, but I can't stress enough, no matter how long our universe may last, our multiverse, you must keep paying your taxes. I think right over there.
Yes, I wanted to say something about the Anthropic Principle. It's always described in terms of very narrow tolerances on any one parameter. But Vic Stenger, among other people, have shown that if you vary several parameters at once, you may get very strange universes, but they still have complex matter, or should. And also, there's actually another paper out with describing a possible universe with complex matter, and there's therefore possibly life, that doesn't even have a weak nuclear force. So I think that the range of variation is really much wider than most people think.
Well, even if you have even if you have a universe where it's hard to have a Goldilocks zone, these Goldilocks zones that Andy showed, around stars, perfect for water on the surface of a planet, we now realize that it's highly likely that there are oceans still in the universe covered with ice, worlds like Europa and Enceladus. We now believe that there are as many as a dozen worlds in our solar system that could be abodes for life because they have liquid water under conditions that have some energy. So even if the Earth weren't here, which means that almost all of the solar systems probably have some even if the star is not stable, even if there's no Goldilocks zone. If matter condensed and there's a snow barrier and there are ice worlds, there's probably something that could have life in almost any solar system.
Yeah, this is a very, very good question because we don't know enough about the conditions that are necessary for life to know whether or not there could be other islands in the parameter space of the multiverse where very different kinds of life could evolve. I think we need to exercise due humility here and recognize that we don't know what would happen if you change multiple constants at the same time. People like Victor Stenger and others are just starting to think about this. It's definitely an open question. These are why these questions are so exciting. There's so much more to do.
Of all the exciting photos that I've seen, the Viking lander and so many others from our space program, the thing that jazzed me the most was the image of an ocean, shoreline, clear river patterns, mountains on Titan. The Huygens space probe showed what are clearly oceans of methane and gasoline and mountains made of wax overlying ice. I mean, if there are living beings there, they would be made of wax. And we, some of you in this room, will live in a civilization that actually goes there and finds out. I'm hoping almost all of us.
Okay, so maybe we'll take one more question.
This guy's had his hand up
Yeah,
relentlessly.
let's bring it up front, and then with him we'll finish up.
Hi. So, talking about the universes inside black holes or being created by black holes, if that were the case, and our universe were inside a black hole, or any universe like that, wouldn't there continually be more stuff in the universe? Like it would be expanding, but not only adding space, but matter as well that's coming through.
As well. Yeah, Andy, you want to tackle that?
It's an interesting question, what the relationship is between the inside and the outside. And there's a certain question, it could be very, very much that we were kind of screened off from anything that's happening outside. In the cases where a singularity is formed and a new sort of universe pinches off, the relationship between the parent and child might end. So in that case, you might not be dealing with an influx of new matter. Let's say there are other more complicated ways that space-time can be intersecting, like wormholes. It very well may be that if stable wormholes exist, then indeed you could see an influx of matter going through from a distant part in space and time. And if you're asking the question about our universe, we certainly don't see evidence of giant agglomerations of matter appearing out of nowhere. So maybe that if we're inside of a black hole, we're not necessarily at the other end of a wormhole. But these are all very interesting open questions, and it's certainly a fun and exciting thing to think about. And it's actually amazing that you can think about these things, and then you think, okay, wait a second, how can we experimentally test for the existence of wormholes? Particles of matter would be traveling in slightly different ways around wormholes than around normal black holes. This is something that astronomers might eventually be able to detect. And if those are detected, not only would that be Nobel Prize winning, it would be the kind of a thing that would allow us to realize that some of these places, which seem inaccessible forever, are actually not necessarily in principle inaccessible. I certainly hope that the universe ends up being a place where the ideas we can think of are also ideas that we can test. And that's an aesthetic bias. I don't know if that'll be borne out, but it certainly would be a little bit more kind if the universe wasn't playing a cruel joke on us, that we can think of these things.
So let's all turn to the simulators who are running this simulation
and thank them
tell
very
them,
much.
Hey, how about it here?
Thanking our sponsors.
Always turn to the third wall all the time, because that way you can tell the simulators, I know. And we never got around to much about theology, but that's another time.
So see you all on August 11th for the next Sci-Flix movie and next Arthur C. Clarke Center for Human Imagination event. Thank you all for coming.
Thank you. Thank the panel. Thank you very much, guys.